Welcome to the FinEst Twins Masterclass series on digital twins. My name is Timo Ruohomäki. I'm from Forum Helsinki and acting there as a program director for IoT and data. And in this webinar, we are taking a closer look on energy simulations and modeling, how that is currently implemented in the digital twins and especially CityGML world. And the topic, of course, fits well with the current Green Deal and climate initiatives. And because of that, we wanted to dedicate a full session on that topic. The FinEst Twins project is part of the Horizon Teaming Instrument program, where Helsinki and Tallinn together work on the digital twin city concept. This is a 7-year project with a total budget of 32 million euros. About half of that goes directly to the research and piloting. And we seem to have nice attendance today from both the cities and researchers from the universities. And this is exactly the goal of this program. Some housekeeping things during the presentations. Feel free to share your questions and comments using the Q&A button function of Zoom, or of course chat is also working for you. And we can then stop after each presentation for a moment and check what kind of comments you would have, and continue like that. But I think we can get started. So we have an interesting session of 3 separate presentations, and we are starting with an introduction and a backgrounder for the energy implementations on the digital twins, and that is provided by Professor Volker from the University of Stuttgart, Technical University of Stuttgart. And over the past years, he has had quite an elemental role in especially energy simulations and energy ADE development. So we are quite happy to have you as an expert in here. We have a bit of thing with a Zoom today, so I will grant you the host right, and then you should be able to share your screen. So the floor is yours.
So thanks for the invitation, and my idea is to give a kind of a more theoretical background on the developments over the last years we did with digital twins or 3D city models and use them for energy simulations. And then in the second part, we have some more practical examples of a joint work we did this year with the city of Helsinki with Jarmo's group. So that's Stuttgart. You can see here the advantages of a 3D city model, because you get an impression of the 3D environment already. In the center, there's my office. So that's our university, HFT Stuttgart here. It's online available. And that's a service provided by the city of Stuttgart. So it's already in practice since years. One question is, what problems can we solve with digital models? Because we usually, from geoinformatics perspective, or my background is in computer science and then geoinformatics, we do not build buildings or something like this. We can only provide information and data. But of course, this is not per se, but it's to support others to solve problems, or to solve problems with data by citizens and things like that. So you see clear two big trends. One is in technology, in digital transformation, Internet of Things, etc. And the other trend is that more and more people live in cities. So for this climate and energy transition, cities are crucial. And that's a driver for me to say, okay, well, how can we combine these two things, cities and technology, to develop and support climate protection and the transition to climate neutral cities. And it's not only technology, it's also the people. So it has a social change as well. And that's why I like this term of digital twin or smart cities, because it includes all these three components. It's cyberspace or digital systems. You have the real world, the physical system, and you have the humans living in this real world. And classical urban planning is between the built environment and the humans living in the built environment. But we focus more on this part, digital representation of the real environment in a digital system, by say surveying plus sensors mainly. And on the other hand, of course, these digital systems are used by humans, and humans are taking part of it. One nice example from my perspective, if you think about it, is a cadastre. Because cadastre is nothing that it's relevant for the built environment, but it's a legal system, so it's only for humans. You don't see cadastral boundaries in real world. They are kind of artificial, and they are just used to define and secure ownership. So that's a classical link between physical systems, the built environment, human system, the legislation, and the digital systems. So my main focus is on the what we call this boring term 3D city model since years, and have here a representation that's a little bit scientific, a representation of all objects we are interested in our domain. Not everything to the detail of a molecular structure or something, but to a detail we deal with this data. And that sounds obvious, but it's not so easy to define that. And that's why we talk about multi-resolution models that represent the same thing in different detail for different purposes. And it's mainly the built environment and the environment in say like air quality, fine dust, noise, in this built environment or within the city boundaries. And these models can be used to do predictions with simulations or with statistics or artificial intelligence to not only represent the city as it is, but also the city as it could be in 10, 20, 30 years with different aspects. And that is also, I would say, what is new with the term of the digital twin that we have not thought of in detail in the past is also actors. We started with a 3D representation of the 3D geometry. Then we integrated sensors into the model. And in future, I guess we will also include much more actors in the model, a digital system that controls or steers the built environment. At some part in traffic, for example, we already have this since years with traffic control systems, but I think that will grow and grow in future. And that is also something where I would say from this way of thinking here with data, data will lead to change of behavior by citizens. Just by giving information, you can change the behavior, or people will behave, hopefully will behave in a different way, because we can make consequences of decisions much clearer. So this is not new, but what is new is that we can condense everything in one model, because we talk about huge amount of data. And in the past, it was specifically to different say purposes. That's why we call it that silos. Yeah, there was data on traffic, on buildings, on environment, on urban green, etc. And now where we are in the process to merge everything, because there are a lot of potential in applications where you don't think in these silos anymore. Yeah? Most of the problems we face affect all disciplines in that sense. That's the idea of this urban platform or digital twin, where we have roughly, I will not go through all these boxes, but just give a rough overview. On the bottom, we have the sensors, IoT things, cyber-physical systems, can be satellite imagery as well. Then the green box, we kind of need to manage all this data and integrate it. And on top of this data, we build application services to analyze the data, to visualize the data, and to build APIs to work with the data. And on top of this, we build business services and that is domain specific then. Yeah? So there would be applications from energy perspective, for example, where I'm interested in. And then on top, of course, you have the humans, the consumers and citizens, visitors in the city, and so forth and so on. Yeah, and yeah, so I'm mainly focusing on this energy part with simulations and visualizations. You will see later what that means. Yeah, the general idea, and that was one project we did some years ago with the county of Ludwigsburg. That is a large area. It consists of 34 communities in our state of Baden-Württemberg. And with this 3D model, we can say roughly estimate CO2 emissions per sector from private household, public administration, industry, transportation. And in the idea of this climate protection plan, of course, was to define say an overall strategy to reduce CO2 emissions, but not just an overall strategy, and then take specific actions to reduce it. And one of these say data product is that we developed a simulation to calculate the CO2 emissions by heating per building, power consumption per building, but also possibilities of using renewables like photovoltaic on buildings, and use this as a basis for this climate protection plan. Yeah, with all the difficulties like data available, cost of data acquisition. Of course, the model is not for free, even with the open data. Someone has to capture it, so that can be costly, of course. Data privacy, we talk about individual households, so data privacy is an issue, but also some technical issues is, of course, the simulation. We need to find a good compromise between the accuracy of the simulation and the time resolution of the simulation. Do we calculate it on an hourly basis or on a minutes basis or on a monthly basis? And this, of course, has an impact on the performance of the simulation, because we want to be able to calculate this for a district, not only for a single building, or in this case, for an entire county with 34 communities. So it should not take years to do this calculation. And of course, there's a relationship, and it's always a compromise between simulation, performance, and accuracy of the simulation. Yeah, the different, say, components or building blocks of this whole project or the general methodology is we need a 3D city model, we need to have the simulation, as said, we need to visualize the data so people can understand it. And we need to integrate sensors and measurements in such a system. If I'm right, CityGML was introduced in the last seminar, or the last seminar of this series. Just to give you a brief overview or a reminder, in CityGML we represent the built environment and many other things in a city, at least in theory. There's a data model behind this CityGML, or the city model, and that is defined in CityGML. Everything is a city object, and all city objects together are the city model. And a city object can be a building, can be a street, can be terrain feature, can be water elements, can be vegetation, can be bridges, etc. So all kinds of things that appear in a city. Street furniture as one module is grouped in a way that you have this semantics there for every object. Okay, that's the building, and then you get some more detail. It's in a way a building has a function, so it's a public building or it's a private building, residential building, whatever it is. Yeah. So you have a lot of semantics in this model based on this CityGML data model. And in addition, every object can be represented in different spatial resolution or detail, and that is called city as a level of detail. On this slide you see one of our university buildings in this different level of detail. A level of detail 1 is an extruded footprint, so you have the average height of the building and extruded based on the footprint. Level of detail 2 is adding the roof structure. Level of detail 3, adding facade details like windows and doors. And level of detail 4 is adding the interior of the model. Yeah, and if you look at real world models, you will usually find buildings, terrain model, and the public trees, yeah? The vegetation, but usually not the vegetation of the entire city, but only the vegetation that is owned by the public, so no private trees involved. Yeah. But there are initiatives to extend it and to add more objects, and then we tend to call it a 3D landscape model. But it's more a question not how to store it, but how to capture it. So, and then we focus on the building model for now. And one here you see again this different level of details. There's a level of detail 0 as well, which means you have the building footprint as a 2D element in a 3D environment. Yeah. So even if it's a 2D footprint, it has 3D coordinates. Yeah, so you have the height of this footprint. And the rest, okay, that's what I already said. And in the new CityGML, this concept will be changed a little bit because in several applications, it's, say, a limitation that you have interior of the building only in LOD4. So you need to have detailed facade structure already before you can add interior of the building. And that was seen as a big disadvantage because, and that's true for the simulation world for sure, you also want to be able to represent buildings like this, yeah, with an LOD2 model, but with interior structure as well. Yeah, that can be used for simulation or for indoor navigation and things like that, or for 3D catastrophe. I think windows are not so important, but you need to be able to subdivide a building into stories, rooms, etc. Yeah? So that's why this LOD concept will be changed in CityGML to be able to have interior models also in LOD1 and LOD2 and LOD3. Here's another example that is, I think, also important to understand in contrast to CAD and BIM world. We focus on the objects you see, yeah, like walls, ceilings, floors, and rooms, bounded by wall, ceiling, and floors, while in CAD and BIM model you focus on, say, the concrete elements, which is a wall in 3 dimensions, with inside interior, etc. So from my perspective, it's complementary. If you add what you have in the BIM model as empty space, you have in the CityGML model as an object room, like this. But in the CityGML model, we usually do not have these volumetric elements, so we have empty space where the walls are, because we only capture the surface of the wall, not the interior. And if you merge both, you have the complete picture in that sense. Availability of 3D models, I briefly try to summarize it in this example. You have 3D models on municipality level, like Stuttgart, Rotterdam, Helsinki, and many other cities. You have less detailed models on state level, at least in Germany that's the case, but I'm in many other countries worldwide, that is the same strategy, because on state level you need to ensure that you have a more or less fully automatic procedure to derive these 3D models. Otherwise, it's very difficult to maintain these models. And then on European level, the 3D city models have become part of the European geospatial data infrastructure with the Inspire NX3, because that defines a 3D building model as well. And NX3 is, say, mandatory since this year. So we will see also on European level, hopefully these 3D city models as part of the Inspire data infrastructure as well. So to summarize, data is available on these levels. So how can we use this in our application on energy simulations? And for this, we need much more details on things that are not part of this base model or the CityGML model. But CityGML allows for an extension, and one of these extensions is the energy application domain extension. It's called, or in short, Energy ADE, where we add objects and attributes that are relevant for this energy domain into the CityGML model, so we can make use of this. And this is roughly spoken thermal zones, because in simulation we talk about thermal zones, not necessarily about one building only, but thermal zone can subdivide a building into areas where we have the same thermal conditions. Construction material, that is something that is more or less missing in CityGML, and in the BIM world, there are a lot of information available, but on city scale, we usually do not have this information, and we have no data model to store that. So that is something we add here to the city model. Energy systems is another part. How is the energy used? Occupancy and schedule, of course, that's another important aspect for simulations. Yeah, we need to know, or the use of energy in a residential building is very different from one in a public building, for example. And time series, that will be, this extension is based on CityGML2, so several elements are also becoming part of the CityGML3 model. But in general, it will not change the needs. Yeah. So we have here the thermal zone. I will just roughly skip this or briefly go over this. We have physical characteristics of the building construction, like U values that are relevant for heat transfer. So essential parameters for the simulation based on the material used to build the building. Then we have the, for the simulation, most difficult part, the occupancy and the use of the building, which changes over time. One simple element can be set point temperatures, so we can store what temperature is intended to have in the building, the 22 degree or 21, and what does it mean if you change the set point temperature in your model. But it can include many other things like operation schedules, using of domestic hot water, etc. So many details that we do not really know, and we do not want to know too detailed, but need to have a good estimate. And then the energy systems to model how this energy is generated. Yeah, is it based on oil, gas, solar thermal, heat pumps, whatever. So this needs to be represented as well. So this is the energy ADE, and time series obviously need to be supported for this. So with this, we have an idea of the data model. And now how do we use this data model? We calculate in our tool, as I said, this is compromise. We calculate on a monthly balance the losses and gains of this building, of every single building. Yeah, we want to know the heating demand and domestic hot water. That is also taking energy to create. We have internal gains. If you invite guests, you have internal gains because you generate heat, or a cat. And then we have solar gains, of course, on the building, on the roof and the facades. And we have transmission heat loss from the building to the air, because it's cold outside. You will lose heat to the air. And that strongly depends on the used material. So we need this information. And you have losses due to ventilation. You want to have fresh air from time to time in a building, and then you need to exchange air and have energy losses, or gains. Depends on the part of the world you live in. But that's a general idea, and almost everything depends on the volume of the building and on the hull of the building, the walls and the roof. And all this we have in the 3D model, and we don't have in a 2D map. So that's why I think the 3D model is a really big gain for this kind of simulations. And the difficult part, as I said, is this the occupancy modeling, because that's not a deterministic process. Yeah, if the building construction is deterministic, but the occupants' behavior without monitoring every citizen, that we don't want to do, yeah, we have to treat it as a stochastic phenomena, which makes the simulation little bit difficult. But you have to deal with it. Stochastically means the simulation run does not always give you the same result. If you have some stochastics in the simulation, your results are within a given range. So you have some uncertainty in this simulation, and that's mainly due to the unknown occupancy behavior. If you're interested in detail, there's a PhD by Parag finished this year on how to model the stochastic part. And now if we put everything together, and that is what we did in this tool SimStadt, we developed this simulation process that is going through all this, say, details on loading a 3D city model, extracting or grouping buildings by saying, okay, we have residential buildings, whatever. But geometric pre-processing calculates the volume, calculates the areas to the outside, calculate areas to neighboring buildings, because you do not have that big heat loss between different buildings. Includes the building physics, the usage, etc., etc. Yeah? And the result is some intermediate results with all this geometry interpretation, and I will go through this later. So the results is then you have the heating demand, you have you can calculate photovoltaic potential. These are different workflows. You can do district heating layout, and if you don't want to display the heating demand per building due to privacy, you can also visualize it as a heat density map. Yeah? And then we can also calculate scenarios by saying, okay, what happens if we have a refurbishment rate of 1% in future or of 3%? How do we reduce the CO2 emissions, or how do we reduce the heating demand and the related CO2 emissions by that? Yeah? So this is something that can be done in this simulation. And just to go back to this example as a say reminder that there are some issues in this process. First issue is data quality. Yeah. We always assume that we have perfect building geometry, but unfortunately this is not always the case. Yeah. So if we have a solid geometry, then we can calculate the volume, no problem. But if we have small errors in the building geometry, like a polygon that is not planar, or like a small gap between the polygons, then the question is, how does this affect the calculated volume? And that is essential for us, because if we do some wrong calculations here, that has a big impact on the simulation results. And here we did some experiments where we insert specific errors into the geometry, and then we calculate the volume, and you see, especially in this case, it has a big impact on the calculated volume, and the large one as well. And the last one, here we have a large hole in the geometry, and then we can say, okay, that's obvious that this has an impact on the geometry. It's obvious. Then there's something missing in the geometry. But the last part, there's just one very small error that visually you do not necessarily see it. That's a change in the orientation of the face. So we assume that every polygon is specified counterclockwise, and here one polygon is specified clockwise. And that has a very big impact on the volume calculation. Yeah. And why is this? This is one simple example for calculating an area of a polygon, but it's the same in 3D, but it's easier to illustrate this in 2D. Yeah, to calculate the area of the polygon or the volume of a solid, you take a reference point, take an edge of the polygon, calculate the area of this triangle, and depending on the orientation, you add or remove this area to the area of this polygon. So here we will add this part, we will add this part, we will add this part. With the next edge, we will remove this. With this, we will remove this. And then in total, we have the complete area of the polygon. And that's a very fast, very simple algorithm. And the same, it works to calculate volume in 3D as well. And it's very sensitive if one of these orientations of the polygon is wrong, or here of this edge, then you do not add the area, but you subtract the area. And that's why this errors in the orientation lead to large errors in volume calculation. And that's why we spend a lot of time in quality management before we do the simulations. Yeah, you can find details here, but that is very essential for us to do this geometric validation of the models to ensure that we do not run into these problems. And the other question where we do assumptions is we estimate, because we don't know that usually in 3D city models, we estimate the used material by the Episcope or the tabular database, which gives information based on building type and year of construction or refurbishment to derive typical used materials in that time for this building type. Yeah, for example, if we have a single family house 1980, we know, okay, that is most likely concrete or things like that. Yeah, so then there are details on the U values, etc. Yeah? And this is another assumption we do in the simulation because we don't have all this information on a city scale. Yeah, that may improve in future with BIM models because there it's integrated, but we have a lot of old buildings that we have to take into account. And these are, from energy perspectives, the most interesting ones. Yeah? The new ones are all good. Yeah, so then we did all this calculation on this district of Ludwigsburg, integrated citizens, etc. Yeah. Now, next part is the visualization. Yeah, we want to show the models to the client, to the citizens. And one very simple architecture is take the 3D model, convert it to 3D tiles, visualize it on a web browser. You can find a step-by-step tutorial here how to do that. We had a workshop in Delft last week. And that's simple, and it's fine for a small area. But if we don't want to do it for one project only, then we need to have kind of a standardized way to do that, and an API to get access to this data. And that is currently under development with the OGC 3D container, or with this 3D portrayal service that is already an existing OGC standard that provides you some standardized query or API to access this data. Yeah, and that is here displayed. There are several OGC standards, and this is how they belong together. The 3D portrait service specifies the API or the query interface, and 3D tiles or I3S, they define a data format that can be used to stream the data in the internet. Then you can build this visualization pipeline from the CityGML data, select the data you're interested in, map it to a streamable data format, and the client can access, depends on the client, if it's a cesium globe, or then it can render 3D tiles. If it's S3 client, that S3 client usually prefers I3S. So that is how you can select these things. And here's one example how this query looks like. You have the get scene request that gives you the 3D scene, and it's in the 3D portrayal service. You specify a region you're interested in. You say which format you want to have. Here 3D tiles. You specify which layer you want to have, buildings, and the level of detail you are interested in. And then server gives you this information in S3 tiles. Or here's another example, similar region, but here we are interested in the point clouds layer. So this is how you can build an interface to do this visualization and integrate not only the buildings but additional data into the model. And it can be, like in this example, also simulation results from a wind field simulation, from a CFD simulation. You would see examples later by the Helsinki use case. And on top of this, there was a big shift in the OGC to develop a simplified API, a RESTful API that is in line with the entire OGC API development that is ongoing, to have similar functionality as a RESTful API that simplifies access for web developers. And let's see, maybe I can show you a quick demo. This looks like. That's our contribution to these. There were 3 pilots this year at the OGC to develop a draft of this API. And now we have here 7 different servers that all provide data using this API. This one is the server we have developed with load collections. You inspect what data is available on the server. And so it's like a catalog in that sense. And for example, here we have some data of New York in 3D tiles and in I3S. We have some CityGML or from CityGML D1 data from California. We have a model from CDB, from a simulation database from San Diego. We have terrain, San Diego, road elements of San Diego, etc., trees. And if we, let's say, select this data set, we will be projected to San Diego, and hopefully we'll get some 3D models. That unfortunately is kind of here we have the models. So they will be loaded. Okay, we have to work on the viewpoint. So now you see the San Diego data set, or in this case, the LOD1 model of San Diego is loaded tile by tile in this streaming format. And then we can add kind of a sensor data to this model. Oops. Or we can go to another server. This one is a server from Cesium. Here you have a worldwide 3D model available that you can load. You have a very detailed train station in, I think it's in New South Wales, where you have very detailed models, a very detailed model from a BIM model of this train station, including street furniture, lamps, whatever it is there. And you see a lot of details here. So this is also possible and supported in this kind of visualization. And what the role of the API is in the end, that you can search on servers, find models, and request them in different formats, in a standardized way. If you do not follow the structure of this API, we would not be able to find the data on the server. And last example, is again in, oops. I want to say it's again in Manhattan. Need to go there. We definitely have to work on setting a viewpoint in at the right place. And if you can also select specific parts of the model where you say, okay, I'm only interested in this part because that is the district I'm working with. And then you fetch only the 3D model of this area. That is a little bit slow. Maybe it's because everything is streamed. Let's try again. Anyway, sorry, that was not as it should be. You should see some 3D models like you have here. I messed up something. Sorry. Anyway, so you've seen the results and hopefully get an idea what is the purpose of this API. And just to finish that, you can integrate. Then you can attach sensors to specific buildings. Here we use an integration of this 3D visualization part plus some sensor data monitoring PV potential or PV power generated by PV of a building, and then connected using the SensorSyncs API, which is another OGC standard that grants you access to the sensor data. And then you can visualize, for example, integrate air quality data to your 3D model based on measurements. Yeah, so that is the aim of this integration of 3D city models plus sensors to be able to view sensors in the 3D environment as well. Yeah? And for this, we need to have a way to connect these sensors, and this way is the SensorSyncs. Yeah, with I would say, due to lack of time, I will not go into details how to do this in a technical way, but it's basically we take an object that we have in CityGML and connect it and attach a sensor to this object. Yeah. And smart cities need smart people. Yeah. So all this work was done in several projects in our research group. And by the way, that's why I want to share this. We were participating in the World Challenge Finland 2 years ago, which was really nice. And I guess that was where all this initiative with Helsinki started. Jarmo will talk about later. Yes, that's it from my side. Thanks for listening. Sorry for that I messed up the demo a little bit. You will find videos on the video on a YouTube channel. The link are in the slides. Yeah, so thanks for listening.
Okay, thank you. That was very interesting. Lots of new points also, and actually the presentation is or the demo is interesting from the point that since we are working with 2 cities and creating like an umbrella on top of 2 cities and 2 city models, that is actually something that is quite worthwhile to think for our researchers. Since we have some researchers from both Taltech and Aalto attending today, what kind of innovation do you see, or room for innovation do you see in this field, what might be the next steps in the research that should we put interest on?
Yeah, that's a very good question, and of course, interesting and very relevant from my perspective. What we plan to do in the next steps, besides what we already did in the past, is that we currently we do the simulation on a monthly basis, but we see more need to go to higher time resolution. So, and that leads, and we have some plans to do the simulation for a larger city or larger district on a, say, daily basis or even hourly basis, to see the independent or the links and dependencies. For example, that's not so much related to heating demand, but on water, we see a big change in due to climate change, that we have much more heat stress, but not the entire year, but only a few days in a year. But for this, it's very essential to have a not this monthly estimate, but a much higher time resolution. And that leads to much more data. And that, to answer the question, to be able to analyze this kind of data, I think we need to develop much better visual interaction. Currently we present the data in that sense, but I think we need to have much better tools to enable people to analyze the data. And we need to have tools web-based, so we need to solve the streaming problem for time-dependent data sets. And this interaction between humans are quite good in detecting correlations and things like that in a visual way. And currently we all do this on black box machines. But I think it's really a challenge to, and I think we can gain a lot if we kind of find a good mix between some analytics on the server side with no human interaction, but also some tools that support human interaction and display the data so the humans can see and analyze the data set. Because I think humans are quite good at that as well.
Yes, and it is of course elemental when looking for behavioral change that we need to look for that interaction quite a lot. We have a question from Einar Kiesel. Can you integrate also online electricity consumption data into the model? And there is of course a cross action between electricity and heat.
Yes, yes, we have this done in one use case with the city of Wüstenrot. The main difficulty is not so much to integrate it. So in Wüstenrot, there's one Energy Plus district, with a agrothermal, so with a central, with a decentralized local district heating network, agrothermal, plus lot of PV, and we monitor heat production, power production, heat use, and electricity use. And then it can be used to control the battery storage and how much power you give to the grid, etc. So integrating is using the SensorThings API is quite easy. The biggest challenge is that we usually are not allowed to have access to this data because it's private data. But in this case, some citizens donated the data to us for research purpose.
That was actually his second question, that how do you overcome the GDPR issues? But I also think that the consent is quite critical.
Yeah, in this case, it was some citizens have a high interest in technology and as I said, in a way, donate the data.
Yeah, good. Okay, thank you. And this has a very nice agenda today, because the next presenter is Maxim Rossknecht, who has been doing master thesis for Professor Coors, but he is doing it for Helsinki. So this is like a nice bridge between Stuttgart and Helsinki as well. So now I would like to ask you to transfer the host to Maxim. So if you go to participants and click on Maxim, and there is the make host or something like that. It's a bit self-service today because I probably set this webinar in the wrong way. See if it works. So that is why. Do you see it, Volker?
If you click on my video, the 3 dots, and then you can select me as host.
Do I need to do that?
Yes, yes, you need to do it.
Okay.
Sorry. So select Maxim, and then there is the make host.
Okay.
Okay.
Yes, good. Now you should be able to share your screen.
Yeah. Okay.
Mute.
So you should see my screen. Yes. Welcome from my side. Thanks a lot for the presentation from Volker course about the concept behind all my work. So I have to not to go too much into backgrounds and can start on implementing the Energy ADE on CityGML, which I did in my master thesis. And the master thesis was this year about the concept and the evaluation of the heating demand prediction based on 3D city models and the Energy ADE in a case study of Helsinki. So I did this with the city of Helsinki and the Helsinki city model. May I introduce myself first? My name is Maxim. I'm 24 years old. I did my bachelor's and my master's degrees in the University of Applied Science. And I'm now currently working for the Fraunhofer Institute for Computer Graphic Research. As an introduction to this overall work, I want to talk something about the carbon neutral Helsinki 2035. And the carbon neutral Helsinki action plan assumes that more efficient buildings can reduce more than 80% of the emissions of greenhouse gas emissions. And as Helsinki only owns 11 out of these 80% reduction potential to reduce the CO2 emissions caused by heating, it's up to motivate the owners for more energy efficient buildings. And one problem is here, which building have the greatest potential in reducing CO2 emissions? Because if we know which buildings these are, we can probably support the owners of these buildings more than other ones. And the hypothesis of my work was with a heating demand simulation, I could achieve the accuracy of 20% compared to measurement values, which sounds at first a bit much, but 20% would be quite good because we cannot simply model, as Professor Coors already told you, the occupancy and the interior of the building, which is also influencing the heat demand. And based on this simulation, we could calculate the refurbishment rate, which is needed to reduce these CO2 emissions caused by heating by 80%. As an overall picture of my work, I have here this slide about which is structured in the data preparation, the simulation itself, the evaluation of the results, and afterwards the result visualization. And in the data preparation, we have here the Energy ADE integration. So we have a city model from Helsinki, and we want to join this with the Helsinki Energy and Climate Atlas, which contains attributes which conduct the heat demand. So like, for example, the number of floors or the usage areas, or also the number of occupants and so on. And these are all information which are conducting the heat demand, and we can use the Energy ADE to store these inside the city model in one database. So we don't have 2 or 3 data sets. We have one data set which is on a common data model and then can be used for the heat demand simulations. As we also already heard, we need some building topologies which represent the finished this building stock in Helsinki. And the Tabula project, which was mentioned before, which provides such information about U values and thickness of walls and construction parts. The Tabula project does not provide any data for Finland. So we need a specific library which represents the Finnish building stock or the Helsinki building stock to simulate the data. The library needs to be defined first. Afterwards, you use this information, which is all stored in the CityGML database in this case, and a connection between the simulation environment and the database is established. The heat demand can be simulated, but also refurbishment scenarios can be applied, and the results are written back to the database directly with the usage of a new workflow step from the simulation software, which directly inserts the simulation result to the database. Afterwards, I have done a validation or evaluation of the simulation results. Therefore, I have 2,000 consumption data for heat demand and electricity and water consumption, which is public available for Helsinki-owned buildings. And to visualize all these results and have a benefit out of it, we need we have created a 3D web visualization to explore Helsinki in 3D and get all these data which was simulated. So coming to the data preparation, as I told you, we have the city model itself and the attribute data, which should be stored in one model with the Energy ADE. And before we can join these and bring these all together, we need to set up the Energy ADE inside the 3D CityDB database. And the 3D City database is a CityGML database, which is in this case based on a PostgreSQL database. And to use the 3D City database brings already a tool, the database importer exporter tool, which is able to transform the schema definition files from the Energy ADE to a schema mapping for the database tables. And if we transform this data, the Excel file, XLE file from the Energy ADE, we can then register this schema mapping, which is generated through the transformation process to the 3D CityDB. But so we have all tables which are needed and relationships which are needed inside our database, but we cannot import in or export CityGML files from the database because the features are not known to the importer exporter tool. And therefore we need to apply or add an extension, in this case, extension Java library, which is then able to import and export the database, the data inside the database with the Energy ADE. And this extension was provided from Virtual City System, and so I don't have to do this. But it's also possible to write your own extension, and there's a tutorial if you want to. So, but bringing all this data inside the database with the Energy ADE, and we have here two different approaches, a file-based approach and a database approach. For both approaches, I use FME, Feature Manipulation Engine software, to do so. And the file-based approach has the principle to read the CityGML files and Excel files with attributes, to rename and create the attributes, define the feature roles so that the relationships between each feature, and write this all back as CityGML plus Energy ADE. This can then be imported to the 3D CityDB. Another approach which I did was to read the CityGML directly from the database, read the separate Excel files, join the data sets, filter attributes, which we want to insert, and insert and update it directly to the database using SQL. As a result, what we get here, in this case of Helsinki, it is possible that if the energy demand is known for a building, so the consumed energy, a building has an energy demand feature which stores in a time series about with the information about the consumed energy. But the building has also floor area, which is later also used. And as also Professor Coors told you, a building has here a thermal zone. In this case, it's a monozone. So because we have no interior modeled in this CityGML dataset, we have just one thermal zone for the whole building. But each thermal zone can be structured in different usage zones. So for each usage, like residential or retail, we can store a floor area on the usage type. For if the usage zone is occupied, I have also stored the number of occupants as an occupants object from the Energy ADE. As I told you, to use all this information for the simulation, there's a database connection established to connect the simulation software between the database and retrieve all this information, which is stored in Energy ADE features and object, and use this in doing simulations. So it's a simple connection which requests Energy ADE features and assigns it to the building. As the usage of the buildings is influencing the heating demand, and as I told you, there is no information about the building topologies already present or already available in the Episcope Tabula project. I had to define the usage behavior of Finnish residents, of Finnish buildings, and therefore I used the German library and modified it according to the energy certificate regulations from Finland. And for example, here you can see the set point temperature, but also the occupancy and the domestic hot water consumption is modified according to Finnish sources. The same had to be done for the Finnish building physics library, and the building physics library is a classification of the whole building stock in different house types, like single-family house, multi-family house, or high towers. And these are all further classified in year of construction ranges. And for each year of construction range, we have a classification in different status. So like original as built, or we have a refurbishment of the walls, the roofs, or the windows, or we can apply energy efficiency, so advanced refurbishment. And all this information is also taken from the Finnish energy certificate regulations. What means energy efficiency in Finland? According to the Ministry of the Environment degree on improving the energy performance of buildings, undergoing renovation and alternation. The original U value must be halved, but not higher than 0.17 watt square meter per Kelvin. And the ground has to improved as far as possible, and the U value of the windows should be 1. So this is all defined in the finished building physics library, which can then be applied to the finished building stock in the simulation software. Of course, the CO2 emissions are influenced by the heating system which is used to generate the heat. And in Helsinki, we have here a special case because 92% of the buildings are connected to district heat. And the Helsinki district heat network aims to reduce the use of coals and shift to renewable energy sources. And so they assume, or they plan to reduce their CO2 emissions to generate heat significantly by more than 80% to 2035. And these CO2 emissions values, CO2 emissions values can be used by multiplying it with the energy demand, the simulated energy demand divided by the yearly global efficiency of the energy system. Another factor which is influencing the heat demand of buildings is the temperature, of course, the outside temperature, and the Finnish Meteorological Institute provides here long-term predicted weather data. And in general, we have, due to the climate change, and temperature increase, but the winters are more affected than summer seasons. And the data set provided here has values for 2030, 2050, and 2100. But I only use the information which is for till 2050. As I told you, it is possible to apply refurbishment scenarios to the finished building stock. And I used here 4 different scenarios. One scenario is only a climate change scenario. So I investigated how much influences the climate change influences the heat demand of buildings. And the second scenario assumes additionally a 1% refurbishment rate per year. And the business as usual plus scenario includes the improvement, or the expected improvements of the CO2 efficient district heat network in Helsinki. And the rapid development scenario assumes a 3% refurbishment rate per year plus the improvements of district heat. So this was all inside the simulation software. And as a last step, the results are written back from the simulation software to the database as energy demand and floor area features. So the energy reference area, so the heat area, is stored as a floor area property, and the energy demand, the simulated energy demand for several years is also stored. So coming to evaluation of these processes, first, how is the Energy ADE integration valid, and how valid is the simulation and the heat demand results? For the integration of the Energy ADE, I conducted here one problem, that the Energy ADE schema was not specified inside the CityGML files after export of the CityGML files, but this was a problem due to the importer-exporter tool, and this was fixed by hand. So I just copy-paste the line here to the file. Additionally, the monthly heat demand is stored in a time interval, and the unit month is not property of the or an enumeration type of the time unit in GML. So so we have here to use the restriction type other month instead of just month. So these are small issues, but yeah. As a comparison, the file-based approach has benefits when you don't need to add a database and you just want to convert your data or bring your data together, but you have not all ADE features on the fly definable, because FME is not capable to have all features which you probably need, like the energy demand or the time series is not a feature inside FME software. So there can be problems here, but it's still possible to manage this. And one disadvantage is, of course, the files are getting large because you have more and more information inside your city model, and probably you cannot open your file anymore when it's too big to read in your notepad. The database approach has the benefits that is simple updating possibilities, can be used in other techniques like Java, which I did, and there's no limitation in database size, so you can store also hourly resolution energy demand values. But usually you have more than one table conducted, so you have to write in more than just one table, which can be a bit difficult. Coming to the simulation results. So how valid is the simulation? We have here the measured energy demand. So the sum of the energy demand measured and the comparison against the German libraries, simulating the heat demand with the use of German libraries or with the use of the Finnish libraries which are created. And you can see for the Finnish libraries, we have here mean absolute percentage error of 80.5%, and for the German libraries of 20.7%. So it's kind of a valid library which was created here. If we use additional information for the simulation, like the usage zone information, which was available for Helsinki, or the heated area information, we have here two histograms which are shown, they show the deviations in percent while using the heated area information or the usage zone information for different usage types. And as you can see, the usage zone information not deriving the correct results in all cases, because they are not they usually don't represent the whole building itself. So there are sometimes missing areas which are not covered in the building in the usage zone information. This is why I rejected this to use this information for my simulations, and I use it only the heated area, so the floor areas information of the buildings, and we have here up to more than 65% deviation plus. This is due to special usages of buildings like healthcare or retail. Are these outliers, and here we have more than 100% deviation to the simulated to deviation from simulation to measured heat demand. And I want to show you why there are so large errors. For example, if you can see here, we have here 3 buildings. One building is highlighted in orange. And the simulation says that we have roughly 180 megawatt hours per annum. And this measured heat demand says we have more than 700. And it's most probably that measured heat demand refers to all the 3 buildings which you can see in this picture. because they are also somehow connected, and this is not correctly modeled here. Also this is so the mapping data of the information about the heat demand, the measured heat demand, is just mapped to one building, which is here in orange, and not for all these 3 buildings. And so we have here more than 100% deviations in the simulation. Let's come to the prediction results. For the business as usual scenario, we have an energy demand reduction of 0.7 terawatt hours per annum. And just for a reminder, we have here 1% refurbishment rate per year. Compared to the 1990s CO2 emission, we have a reduction of 28%. So not this target reduction of 80%, which the city aims to achieve. If we include the improved district heat network, improved district heat network CO2 emissions, we have here already 79% reduction of the CO2 emissions from 1990 till 2035, and this is already a would be already a good target, or a good would be already good. But if we have a reduction, if we apply the rapid development scenario with 3% refurbishment rate per year, we have a 1.5 terawatt hour reduction in heat demand, and the 1990s CO2 emission would decrease about 82%. So we can already see the reduction of the CO2 emissions is more influenced by the improvements of the district heat network than the reduction of the heat demand, which can be achieved through renovations. As a result, I have created a 3D web visualization of these simulation results. I'm going to show you a small video. Yes, it should start. So in the beginning, we have here just overall information for whole Helsinki city, and the same tables as I show you in my slides. And we can explore just for the whole Helsinki information about the predicted heat demand. But you can also show individual buildings heat demand, and for each building you can see the actual simulated heat demand, but also the simulation, simulated saving potentials or the CO2 emissions. If you click on a building, you can explore the climate change heat demand, or the impact of different refurbishment types like roof, walls, windows, or the advanced refurbishment, and what is the impact of these refurbishment types on the heat demand. As a conclusion, the Energy ADE is rated as a data model for Helsinki and for Energy ADE simulations, because it provides the possibility to store the needed information or available information in an open common data model. But there is a limitation in the limitation of availability of consistent data sets. Like you can also see here in this picture, we have here some buildings which are gray, so there's no heat demand simulated. This is caused that there are some information missing, most probably the function or the year of construction. So it cannot, so this is due, so we cannot access the data from the finished building typologies or libraries. The accuracy of 20% deviation is only achieved, or is achieved for 61% of the buildings, and the refurbishment rate to achieve the 3% of greater than 3% is needed to achieve a target heat demand reduction through renovations of 2 terawatt hours. And as I already told you, the CO2 reduction is significantly significantly influenced by the improvements of the district heat emissions. This was from my side. Thank you for your information.
Unmute. Yes, thank
you. If you have information, questions, or you want more information, you can check the paper or the website of Volker Cross, and there's more information. And you can also download the slides or the whole thesis work there. Thank you.
Thank you. Yes, yeah, that was quite good. I think we have one question. What is the biggest pain point in buildings monitoring?
The biggest pain point? Oof. I don't really get the question.
Was there anything that was especially difficult when in getting the data?
Most of the data was open data, so from the Energy and Climate Atlas. But for example, the renovation information is also here a privacy issue. And to have all this information about renovation is maybe one problem. So if we have a building which is renovated, but we don't know it, so we are wrong in our simulations. So this was one pain point, of course. Yeah.
Good, thank you. And we can continue also after Jarmo's presentation. So if you can just pass the host to Jarmo,
of course,
so that he can share the screen, and we will continue with the Climate Atlas.
Yeah. Now I share my screen, and so I think I can take that, and so I start this. So I hope you see my first slide now.
Yes.
Helsinki City also complete, full screen. Yes, thank you. Yes, good afternoon. Yes, from Helsinki or from Espoo. First, I'd like to thank you, Professor Volker, Coors, and Maxim for this wonderful cooperation project. So it has been a great pleasure also for us to work with you. And I think this is a wonderful example of open global standard combined with open data, combined with university and city, and combined with smart people who have the same goal to do something that is for common good and for the ambitious goals and to tackle the great urban challenge of the whole world. So I think this is wonderful use case, and there's so much to learn from this. It's not only the service and the thesis, but it's the way of working and so. Today I like to give a little bit background information of Helsinki city models, little bit talk about the concepts and what are the concepts, and a little bit about city strategy before I go to the Energy and Climate Atlas. Yes, this is our team. This is our Helsinki 3D Plus team. We work in the mayor's office in strategies division. And we are 3 people. Miss Enni Airaksinen, she has worked a lot. This is the Helsinki Energy and Climate Atlas is a great work of Enni Airaksinen. Enni is now on maternity leave, so I'm kind of instead of Enni Airaksinen in this presentation, because Enni knows the Energy and Climate Atlas best, but I do my best to represent this and be here instead of Enni. Together, our team, we have more than 65 years experience of working with 3D. And of course, we have learned something in these years. And I think the main thing is that we are very realistic with 3D. So for us, 3D is not virtual fun or visual wow thing, or pretty pictures for the mayor or something like that. It's a real tool, but it's also a tool that it demands a lot. So working in 3D, it's more complicated than 2D GIS. And when you work with 3D, you must get something added value from the 3D and otherwise it makes no sense to work in 3D. And I think in this project and Helsinki Energy and Climate Atlas, we certainly get added value from 3D. Yep. Helsinki 3D history is over 35 years. I don't go to every point through, but I just want to say that the technology, the modeling technologies, the people have changed there a lot, but it's not a one night miracle for Helsinki. It's a long-term commitment to the 3D work, and also the potential of 3D city models and 3D work has seen, yes, 3 decades ago, and big effort has put on there. So new technologies have come, and our 3D Plus project has worked 6 years now. And in these 6 years, we have made the new generation city models, and it's also very much new possibilities for this. So the vision for the visual simulation 30 years ago has changed to the smart city and advanced analysis and supporting good life and something like that. So cities are practical, cities work for the residents, and the main task for the cities and city servants, I think, is to promote the good life in sustainable environment. So in other words, cities use technology to complete the practical task, and cities' role is somehow to convert the technology, the services and conditions that promote that good sustainable life. So that's our part of this big environment. All right. In big picture of Helsinki city models, we have 2 production lines. We have the reality model, we have the CityGML model. Not going to the production processes and data sources, but I just want to say that these models are not against each other. They are completely different production lines and completely different models over the whole city, but it's both and. So at this point, we see we need the both models. And under the bonnet without the textures, they look like this. I think you know this thing, but I want to say that as open data, the reality model is far more popular than the semantic CityGML model. And it's understandable because reality model is more visual and more easy to use than semantic city models with databases and so. But in analysis, and the complete Helsinki Energy and Climate Atlas is made on semantic CityGML model, of course. Yep. And then about the concepts, and what are the concepts? Even with the professionals in the city, servant discussions or meetings and international meetings, it's a little confusing. People are talking about digital twin or city model or BIM meaning something, and I think every person means a little bit different things. So I like to shortly tell what we think the concepts mean and little bit explain that. First, 3D city model or 3D model, it can be CAD model, it can be game engine model, it can be semantic model, it can be reality model, it can be point cloud model, it can be hybrid of these technologies, but it's a model and nothing else. But when you combine the data with the model, you get a city information model. And of course, CityGML is the best example of this. You can combine kind of attribute data to other models too, but CityGML as an international global standard is the first one. And so yes, that's city information model. And then we get the digital twin. But we see that digital twin is not something on a database or on the storage or data. It's way of thinking and working. So it has the communication with the real world and the digital world. It's combined in processes and services in that way that you get added value from that. It's a way of working and thinking. Digital twin is it's far more than 3D model of a city. Model is a model and like that. And then if you combine open data to this digital twin things, you reach the open co-innovation thing. And that's thanks for open data. And I think this project with Professor Coors and Maxim Rossknecht it's about open co-innovation, kind of open co-innovation. It's also hackathons. It's developer clubs and such things we have in Helsinki also. And then combining all this to cities strategic goals and supporting those we are close to smart city. Smart city, in the core of smart city, there's not the technology, there's the good life for people and the sustainable environment and all this, and this is the big goal of I think every city now. Yes, this is our way of thinking, and we talk of these concepts and terms like this, and I hope that there's going to be some kind of a clarifying thing of these, because it's so confusing now. But yes, let's go on. And city strategy. Yes, Helsinki wants to be the most functional city. This is ambitious enough, I say, but maybe the strategy should be ambitious enough. And this also means that Helsinki is the city that reaches this goal with digitalization. So Helsinki city strategy is 15 pages. And as our mayor was visiting our office, I took the strategy and I overlined every goal there with the yellow ink and numbered them like that. And then I gave this paper to the mayor and said that you can ask whatever number and goal you have there numbered, and we explain how can we support those goals with city models and semantic city models. And yes, number 25 is this the use of digitalization. And Mayor was really enlightened of this technology and said, and this is something concrete, and he believes that we can certainly support these goals with the city model platforms. And then we discussed the topics, and we decided that the carbon neutrality 2035 is the most important, and that was the point that and the first thing that we should make the Helsinki Energy and Climate Atlas. But in city, the reaching the goals is not so simple, and it's a common saying. I don't know where is it originally from, but I have heard it from several sources that 25% of the change is about technology and 75% is cultural changes. Cultural changes are workflows, processes, integrating technology to processes, best practices and things like that, ways of thinking, new way of thinking and like that. 75%, 25, 75. And if you accept this, so I think you are more closer to the change. And there's a big wisdom in these numbers, and that's why and from my experience, I've learned that this is quite right. Okay, and then we reach the Helsinki Energy and Climate Atlas. Helsinki Energy and Climate Atlas is built and made for building understanding about the situation in Helsinki. We are now launching the version 2.0. The 1.0 is 2 years old, and it had the first two modules there. There's the energy data and the solar energy potential data. And yes, the Helsinki Energy and Climate Atlas is the great work of Enni Airaksen, and I think this is wonderful work. The version 2.0 is going to be launched officially in few weeks. It's already up and running. You get the link from this presentation, and you can go there and check all the things I show you. It works there, but it's not officially launched. It's launched in few weeks. I don't know the exact date, but you get the information for that. Helsinki Energy and Climate Atlas 2.0 has the 4 modules. It has the building data, solar energy potential, and the heat demand. And this is the Maxim's part of this. And I think it's wonderful that the thesis work is so ready to convert to the straight for a service for people, and it has the practical side also. I think this is something very special. And then we have also the geothermal energy module there. Geothermal energy is very useful in Helsinki, and it's very promising. And so. And yes, I think Maxim had this circle already, but you see that from Helsinki of Helsinki's greenhouse gas emissions, 56% it's from heating the buildings and heating the water. And that's why the focus in Helsinki Energy and Climate Atlas is on buildings and the heating energy sources and the alternative heating energy sources. And this is the very compressed content of the Helsinki Energy and Climate Atlas. I don't read this. We check the YouTube video clip that is on our YouTube channel. I run it now, and I little bit tell about the content over the video. Yes, in 1.0, the main thing is the basic information of the building. So it's the Helsinki building register there. It has also thematic representations over the attribute data. So there's what's the use of the building year, the height of the building, and more attribute data about the renovations, and also calculated energy consumption before Maxim's work. Every building, and you just click that and you get it. It works on every device. There's also the energy classes of those buildings that have the new energy report, and most of them are Helsinki owned buildings. So you see, it is not the major of them. And also, yes, the heating system of the buildings, and as you see in the small house areas, there are several technologies to heat the building. So there's district heating, there's electricity, there's oil, there wood there, and also there's some older buildings with they have the coal heating system like that. So building the understanding what's the situation now. Yes, the solar energy potential, there's about 1 million semantic surfaces in city of Helsinki city model, CityGML model, and every surface has its own values. You can click whatever surface you see and you get the values there. And of course the walls are as a surfaces, but you must divide or subtract the window areas by yourself, because it should have the LOD3 model of the city, and that's not available. I think it's not available nowhere at this point in the world. But the roofs are very well calculated, and this was the cooperation project with the Technical University of Munich, and this has been a great success. And this is for the private building owners. This is for the companies who are selling the collectors and so. And yes, this is the Maxim's great work here. And you see the buttons there. You see the heat demand there, and the classifying there. You see the legend there, and if you click a building there, the arrow goes there, and what's the situation there. And the effect of climate change. And the heating saving potential and the renovation effect of different things, roof, wall, window, advanced renovations. And so more you have the potential, of course, you see more effect of these changes. And then we have the new geo-energy potential. I think this is wonderful, adding to the service. It has a 150 meter, 300 meter, 1000 meter deep wall potentials. There are the groundwater areas. There are attribute data of the bedrock. There's the types. There's the thermal conductivity. There's the specific heat capacity. There's the density of parameters. There's soil data to support the geoenergy well design. And it has the wonderful swipe tool that you can choose whatever two thematic representations or backgrounds there, and you can swipe there and you can see the difference there. All right, I think this was the end of the slide. And then there are a link collection for you, the Energy and Climate Atlas first there, and then there's the open datasets in Helsinki region InfoShare of the Energy Atlas. There's also the Energy and Climate Atlas video clip that we just saw in our YouTube channel. There's also a compact presentation of this service by Enni Airaksinen. There's our website. You get more information and download information of the city models. And they are also open data sets in the Helsinki region InfoShare. And then the last one is our YouTube channel. There you find video clips, presentations of the general situation of wind flow analysis and whatever simulations we have done. And that was my part. Thank you for your interest.
Okay.
Now,
yeah, thank you, Jarmo. Yeah, it was good ending for this, that we start with theory and backgrounds and end with final service. I don't see at the moment any questions, but I think we could discuss a little bit about the data that has been available. I think it has been even a pleasant surprise how much useful simulations and analytics you can do with public open data. But how do you see the situation at the moment? Is there any important data set that would complement this nicely? Of course, the quality of data is another question, but availability is one as well.
We have discussed about the energy leaks of houses. So if we could have oblique images over the whole city with infrared cameras and then texture the city model with that, and then we could classify the surfaces with energy leaks, and that would be wonderful also. But this is the future. I think now the biggest problem is with the cameras. There are no such cameras that you can take such oblique images yet. But imagine a freezing cold night, -20, and you fly the city. It's very clear whether you get excellent images there, and of course it would be wonderful.
Yeah. There is, of course, as part of the climate change, there is also ongoing discussion about the heat wave and heat waves and how to handle that kind of things, that we have excess heat and excess temperatures. I think this is also for Professor Coors and Maxim maybe, that do you see any additional simulations needed when we are moving partially from heating to cooling?
Yes, at least in Germany perspective, I guess that we have much more cooling in summer than we have now. And with the current situation, unfortunately, this cooling will be done by additionally attached devices running by power, which is not optimal. Or we know from experiments on simulation in Singapore, cooling takes more energy than heating. So that is this one aspect. But what I think is also very essential for a simulation, that's at least the direction we work in, is try to integrate things, what we call food, water, energy nexus. So keep all these things, not optimize them individually, but try to find a global optimum, which is different in that sense.
Yes, exactly. Good. Thank you for this. We don't have any additional questions, so I think we can start wrapping up this for today. I would like to thank you, all the presenters. This was an excellent session, and finally we had the time to focus on one thing, and of course always in that situation it is easy to get more in depth. But of course also for the researchers and for the city contacts, you have the names. You can also be in touch afterwards, and of course especially when thinking about the next research topics and piloting needs, the cities of Helsinki and Tallinn are of course well available at the moment because of many reasons, not only about the FinEst twins. So thank you for the panelists and attendees, and we will continue next week. with urban planning and also the developer angle. So thank you and have a nice day.
Yes, thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.